Yeah, with that little technical hiccup, we're gonna wait maybe 3 more minutes before I get going. Thanks. Who's here, by the way? Good morning. Seems like it might be a more intimate affair, but first of all, I would encourage you to go look at the links in the video description and open the simulation called the PHET, PHET. Might take some time to load, and we're gonna use it pretty soon into the class, so that way you can follow along. Okay, so we're gonna get rolling here. Today we're covering this topic of magnetic induction, and based on the muddiest point, this is probably one of the most intricate process that we do. But hopefully by this point in the term, you've done enough mental gymnastic that you can actually grasp this pretty well. But this is a bit step involved and a little tedious. So let's go through that. So last class, I talked about the analogy comparing electric field and magnetic field, right? There's clear similarities and clear differences, right? The direction is a little funny for the magnetic field, and we have to treat that a little more carefully. But there is some definite similarity between the two things. So let's further this comparison and look at one more step. We know that charges create electric field, and we also know that we can induce a charge by exposing things to an external electric field, right? It'll end up moving the charges and then separating the charges to induce a charge. So can we do the same thing with magnetic field? Since moving charges or current create magnetic field, can an external magnetic field induce a current? That's kind of the question we're going to go for. And to explore that, we're going to use that simulation I was talking about. So for those of you just joining us, please look at the video description below. There's a link to this thing called a PHET, P-H-E-T. It's a physics simulation. And we're going to try looking at the pickup coil tab. It's going to have a coil, right? A light bulb, right? That way you can see if you're making any current, and it has a magnet inside. You can use the mouse to drag the magnet. So try to get the magnet, move the magnet around so to try to get the light bulb to light up. It kind of looks like this. So if you go to the pickup coil tab, and then you see there's a coil and a magnet, right? Lots of magnetic field. So if we use magnetic field, can we make a current? So I'll give you a minute to try that out. You can drag this thing around. How do you make the light bulb light up? So 1 minute starting now. And as soon as you get anything, please share with the chat and bounce some ideas around. So anything? What do we have to do to make the light bulb light up? Very good. Yeah, we do have to move it around, right? It's not sufficient to simply just put the magnet in the coil, right? There's lots of magnetic field in here, right? But just because you have magnetic field exposed to a coil, that doesn't mean current. In order to have the current going, you have to move it. It has to keep changing. You have to keep changing until so that it lights up. And there's the important distinction, right? It's not just magnetic field that makes current, it's the change in the magnetic field that makes current. Thanks for the responses. And yeah, there's a bit of a delay gap, right, between what I do and what I see you type in the chat and when you hear me respond to that. So there's the thing. There's the key thing, that it's the change in magnetic field and we're going to extend this idea of the magnetic field, because when you talk about current, you have a current in a loop, right? So we have an area involved. So we're not talking just about the magnetic field, but in fact we're talking about the magnetic flux, which is just like the electric flux, which is an integral of B dot dA. But the main thing is that you have to keep changing the magnetic field to induce a current. So again, similar but different, right? Very often with this magnetic field stuff. But before we get into the quantitative statement, which is Faraday's law, the direction of this you have to consider quite carefully. And you can see that with another demo that we're going to be doing. Front. There we are. Sorry, that took a while. Oh, it's left, right, mixed around. Anyway, so this is a demo where we have a bunch of magnets, right? These magnets are loose. They don't rub against the side here. They are free to move around. And these are magnets that, if you can see from this little magnetoscope, points north, south, up, and down. So in this case, it's south up, north down in this case, because the red points downwards. And they're all the same. What is different, though, is these rods have different materials. This is plastic, this is brass, this is aluminum, and this is copper. Now, note that none of these materials are magnetic. They're not magnets, right? So, what do you think is going to happen when I flip this thing around so that they all fall? These have the same mass, they're going the same distance, right? What do you think is going to happen? So, give you 30 seconds to put something in the chat and make some prediction. Okay, so I'm going to flip this around, so look very carefully. I'm not so sure how well it'll show on video, but let's have a go anyways. I'll do it again. So did anyone see anything out of that whole mess? They do in fact fall at different rates, right? Which one is the fastest, which one's the slowest? Hopefully you can see that the plastic just falls like regular, right? Whereas way over here with the copper, it seems like it's going slower. It's floating along. So what the heck is happening here, right? So it looks kind of interesting and funny. So let's draw this situation in detail, and then we can talk about what's going on. So what we have is we have a magnet, right? Kind of like this. And we said we had some kind of north-south going in. Arbitrarily, I chose north on top. That means that we have a magnetic field that kind of goes out this way. And in that way. Right? Around the rod. So the rod itself, it's a hollow tube. It's not a magnet in itself, but if you look at the cross section of this tube here, it's like a ring. So it's a loop that can have current going through it. We'll go through all the direction in a second, but with this current, you're going to create other magnetic fields, right? So therefore, you're creating an electromagnet just by the fact that you're falling through. Because as you fall with the magnet, oops. So now that the magnet has fallen a little further, the same loop here, again, north, south, the same loop here will be further away from the magnet. And you have a weaker magnetic field. If I can draw it more explicitly over here, you can think of all the magnetic field to be going through here, like that. Whereas here, you have less magnetic field that goes through the loop now. Right? Because the amount of magnetic field changes, you're inducing some kind of current, and this current acts like a magnet, right? If you have, remember how when you have a right-hand rule, if the current goes this way, then you have a magnetic field that way. So then this magnet will attract the other magnet to slow it down. And that therein lies the whole idea about the direction of this induced current, and brings us to Lenz's law. No matter what arrangement, you expect the magnet to be slowed down by this extra new induced magnetic field. which is Lenz's law, right? Lenz's law is, in colloquial term, it's saying that nature is a bit troublesome in the sense that it always tries to undo our change that we impose on it. But it's not that mysterious. It's not like nature is always just being negative and stopping us from what we're doing. Think of it more like a conservation energy kind of consideration, because you cannot possibly have a change in magnetic field that creates a current, which in turn creates a magnetic field that makes the same current, right? You can see how this will feed into a positive feedback loop and things blow up. But we observe in our everyday life that things don't blow up all the time. Then that must mean the induced current creates an induced magnetic field that opposes the original change. Not the most succinct definition, but the main idea is there. So to apply this Lenz's law and get that direction, it actually takes a few steps. There's no shortcuts on this. You do it just as many steps as I'll do it. You can't think that there's one funny right-hand rule that'll get everything for you. And here are the steps. You have to draw the before and after picture so you know what is the magnetic flux before and what is the magnetic flux after. Based on that, note how the flux have changed. Which has it increased or decreased? In which direction was the magnetic field? Then you can come up with the direction of the induced magnetic flux to undo the change. And then based on that induced magnetic field, use the right-hand rule to find the direction of the current. Quite a mouthful. So let's try with our previous example here. So I've already drawn the before and after picture, right? And for that one single loop of wire on the very top, what we see that the magnetic flux have gone from 3 lines upwards to 1 line upwards. Right, we have less upward B. So to undo that change, what must happen is we must have some upwards magnetic field created or induced in order to undo the change, to try and put it more like the before picture. And then, because it's going up on the inside, then we know that the current must be in this direction. Using the right-hand rule. But in terms of considering the interaction with the magnet, you can think of if the magnetic field points upward, it's like this is the north pole and that the south pole. So then the south is attracting the north to slow it down, to counteract gravity. And because it's such an intricate process, let's do the same thing, but for picture this loop down here. Right? Before and after. So the change here is that you have now more upward speed. Right? Before you're further away from the magnet, now the magnet is closer, so you have more upward speed. So to undo that change, seems to be running out of colors here. Okay. Then the B induced must cancel out some of that more upward, so therefore it must be downwards. Creating a magnetic field downwards, then you can use your right-hand rule to say, oh, the current, if that's the B induced, the current must be this way on the front of the loop, and then go back around the other way. In other words, this acts like a south pole and a north pole, and that also repels the magnet upwards. So both arrangement always opposes what we're trying, the original change, right? In the grander scheme of things, the change that make everything happen is that it's falling downward, so nature tries to partially cancels the falling downwards by slowing it down. And you can see how all the current direction and the magnetic field direction works to make that happen. So back to the demo, why was it that there was nothing in the plastic, but then there was less, it was slower and slower, and being slowest in the copper? Well, the whole idea, right? The amount of magnetic field you create depends on the current. So while you get the same EMF, as we'll see in a second, because these different material has different resistance, right? EMF being voltage, they would induce different amounts of current, right? And therefore give you a different amount of magnetic field to repel or attract that falling magnet. Therefore, in the copper with the lowest resistance, for the same kind of motion, you'll get the most current and therefore the most magnetic field. Meaning then you get the most slowdown. So if we take this to the extreme, what would happen when we remove all the resistance? Well, that thing is called a superconductor. So if you look at that video, also link is in the the description below. I won't show the whole thing just because there might be copyright consideration. But I'll just show the most important part here. You can, of course, watch the whole thing on your own time. Where is it? Right there. Right? This here is already a superconductor slab, and we have to cool it down so that it does become superconductive. This is a little tiny magnet, right? So if you put that right beside there, what happens is, because there's no resistance, the falling magnet is basically inducing as much current as needed to completely oppose the motion. And that's what we call magnetic levitation, or the Messier effect. Again, you can watch the whole thing from start to finish, but that's the key idea there. So that's how we determine, in so many steps, the direction of the induced current. But how much current do we make? Well, that's where Faraday's law comes in. Faraday's law tells us that you have to track your magnetic flux, right? But how fast it's changing in time, right? It's again the change in the magnetic flux that matters. The magnetic flux here is the I guess the sum of the magnetic field going through the area specifically enclosed by a loop. And you can have multiple loops, so we put a big N here. That's just the number of loops. And then very critically, we include this negative sign to tell us that how the direction will work out, which is basically Lenz's law, just to remind ourselves that it is there. But you have to go through the whole process to figure out the direction anyways. And that quantity gives you what we call the EMF. The EMF is like a historical misnomer. It stands for electromotive force. Before people knew what the heck was going on, it's nothing like a force, right? It's just some kind of thing that pushes charges around in the circuit, basically, which we know now. It's basically voltage. In all sense, for our course, in every sense of the word, you can think of EMF as voltage. There's a slight mathematical distinction in the fact that what we thought of as voltage before is a conservative quantity that has to do with if you go around the loop, you don't expect the voltage to be anything but zero. But in this case, if you go around this loop, it is clearly not zero because you're having some magnetic field inducing this EMF within that loop. But in terms of calculation and the units, treat it like voltage, you'll be fine. And that's Faraday's law. So, therefore, in order to get current, to get the voltage to get the current, you will need to have your magnetic flux changing. Well, you can have a few different strategies to change it, right? And so far, up to this point by far, Faraday's law looks intimidating because it involves both a derivative in time and an integration with area. But just treat it bit by bit. In any case, in order to get a change in magnetic flux, you have a few options. You can change the magnetic field. You can change the actual magnitude of the magnetic field, right? You can have this kind of before and after picture, right? You can just increase the magnetic field. You can change the area, right? You can, your textbook has probably shown you can have this before, same magnetic field, and then you have a loop. Then you're moving the loop into it, so you're capturing more of that magnetic field, right? More of the area gets that magnetic field. Or in the case of basically motional EMF, right? Now I'm not going to go through motional EMF in a lot of detail because it really is another way of looking at this whole Faraday's law thing. And then finally, maybe a little more subtly, this dot product here also important. You can also change the orientation. Oh, you can also change the area by actually just changing the area, right? You can go like that to just having a smaller loop. I don't know how you do that, but that's possible. But you can also change the orientation. Have it going flat, then have it going a little bit tilted. Same area, different orientation. You have example of all these things. And in most cases, only one of these things change at a time. So just resolve the dot product first, and then either the b will kind of drop out of the integral because it's constant with the area, and then you can have db dt, or you do the integral and then you take the derivative, whichever. Now, there's one more extension here that we can do, is that your E, right, which is your EMF, which is your delta V, we know it's equal to negative E dot dl integral. It's a loop integral. And in fact, in this case, it's a closed loop. So another form of Faraday's law could be that. This is done around a closed loop. And this is the area enclosed by the loop. So, Leo, to answer your question earlier, maybe the B, the magnitude of B actually depends on time, like it changes over time, or the area could do the same thing. Because time, in terms of integral, doesn't matter, right? It's your dA that's part that we're integrating against. So it's okay that the magnetic field is a function of time. Or even that the total area itself is a function of time, and that's perfectly okay too. So if you want any of the really nitty-gritty quantitative things, I would suggest looking through the video examples that are posted, and of course email me if you have any questions regarding those. But finishing off this point here is that doing this, first of all, notice that this is basically in strict sort of contradiction with Kirchhoff's rules, right? If you go around a loop, you expect the voltage to be zero. But Kirchhoff's rule was dealing in cases without any magnetic induction. Magnetic induction throws that all out the window, and we have to account for the fact that this is also happening. So that's why we're talking about quote-unquote non-conservative electric field now. But the key point here is that this statement tells us that when you have a changing B, you're going to create electric fields. And we'll revisit this towards the end of the course when we kind of look at the other way around, which then ultimately marries the magnetic field and electric field. So your pre-lecture went through in detail what motion EMF was all about. Again, you can kind of treat it as Faraday's law with a loop that the thing is moving across on. It's pretty much exactly the same thing. It's gonna end off with a couple applications so that it makes a little more, hopefully, visual sense to you guys. Now that we can create current, the first and most easiest application you can think of is generators, right? You could, of course, use a wire and just slide across to get a changing area, to get a changing magnetic flux, to get your EMF, but you're going to run out of space. So more likely, we're going to use this kind of arrangement. So you have a permanent magnet set up somewhere, and then you have a loop of wire that you're going to rotate. Oh, let's rotate this way. I don't know. Doesn't really matter. With some speed omega. Right? And as this thing rotates, your orientation between your loop surface and your magnetic field is going to change, right? This changing orientation is one way to change the magnetic flux, therefore inducing your EMF and current. So let's show you one such example here. So here I have a small little light bulb. And then this is one of these simple demonstration hand crank generators. Not one for survival or anything, even though that might be apt right now. But if I just spin it, like inside here, there's coils and magnets. And then if I change that orientation, I get some kind of electricity created. Ta-da! Yippee-doo, right? But if you go back to the arrangement of this thing, this looks kind of similar to something else we've seen. Yes? When you have a loop sitting in a magnetic field that can carry current, that looks just like a motor in reverse. Right? And that's not surprising at all, right? Because a generator is something that changes mechanical energy. We crank it to get electrical energy. Whereas a motor is we supply the electrical energy, and then it cranks and gives us the mechanical energy. So it's not that surprising that the construction is pretty much exactly the same. In fact, I can hook up a generator with another generator to use that as a motor. Let's show you that real quick. Ah, so here I just have another hand crank generator right here. So if I crank that, this thing acts just like a motor. Yeah, let's even get off screen. Other way. Whatever. So the way this works, I think you analyze in detail either in a group assignment or maybe on a quiz question or something. But because of the rotating concept, you can get a sinusoidal EMF and therefore a sinusoidal current as well, right? Assuming that your resistance is nice and simple in time. And this is what we call alternating current because it goes one way or the other. And most kind of turbines run in this kind of circular kind of motion, like wind turbine, hydro turbine, in your coal power plants or whatever, just because then you don't need more space, right? It just keeps rotating in place. And that's one reason why, out of many, that the power generated starts out in AC, and then we transmit in AC, and we have AC everywhere in our homes. But of course, it also has other transmission characteristic that's favorable. And another consideration is, with the motor then, there's this thing called the back EMF of the motor. Because a motor is constructed just like a generator, right? As you supply voltage or current to move a motor, right, the coil is rotating in the magnetic field, so it's also seeing changing in magnetic flux. So then the coil acts like a generator and creates a EMF that Lenz's law opposes the original voltage input. And that's what people call back EMF because it's backwards from what we're supplying. And therefore reduces the current in the coil, and then reduces the torque in the motor. So that's why for electric motors, you have the biggest possible torque when you are not moving. It's kind of ironic. But, this sounds like a bug, but it really is sort of a feature, right? Because with, say, now these electric cars with electric motors in them, they have the highest torque, or what we call low-end torque, at the lowest speed, right? When you're first starting up to accelerate, you have the highest torque to get the most acceleration out, right? So that's another useful idea to keep in mind when you deal with motors and back EMF. And then last but not least, we talked about a speaker as an application to electromagnetics last time. So you can also do the reverse thing, right? You can have the sound move a magnet up and down in the coil, and that generates the current to give you the signal, right? Again, a mic is just a backwards speaker. Technically, only certain types of speaker. There's not a type of speaker that works based on capacitance, but for what we call dynamic microphone, it's basically a reverse speaker. And back in the day when you still have like separate inputs for mics and headphones, and they're not all integrated together, in a bind, you could have just plugged in your headphones into the mic and just scream into your headphones, and it'll work like it'll work like a mic. So that's all I have for you today. Again, all the nitty-gritty quantitative stuff will be done on the video example, but I'm happy to entertain any questions at this point for another 15 minutes or so. So, thank you. So seeing no question, I'm going to sign off here. I will post the quiz on Monday and be a busy bee marking all your midterms this weekend. So see you next week.